So these are some common structures, linear, square, planar, tetrahedral, octahedral. The typical ways that you learn to predict the structure, sometimes they'll work, sometimes they won't work. And so let's take a look at this table here. These are some common coordination numbers of metal ions. And so, we've been talking about the structure and the bonding and all that stuff. But, we really want the full theory underlying this. And so, take a look at copper plus 1. Copper plus 1 can be attacked by two donor atoms or 4 donor atoms. Silver plus 1 can be attacked by 2, but not 4. And so the question comes up is this. Why only 2? I mean, there's plenty of room there. Why not, have this is ammonia. Why not have another ammonia come in here and bind? And another one. And another one, and another one. And so what we want to do, what a theory should do is a theory should give you the description, kind of a visual or mathematical or whatever description of what's happening in here. And so do you feel comfortable predicting? Let's say I'm going to try to find an ion that's not on the chart. What a theory would do is, let's take another ion. I'm going to take tantalum. And I'll add tantalum to this list. Tantalum plus 4. Tell me how many atoms can bind to a tantalum plus 4, or typically bind to a tantalum plus 4. I mean, you'd guess 6 because you see some pattern, but why would it be 6? Why not 4? Why not 2? Why not 3? Or some other number? And so what we want is a theory that gives us a good visual picture of what's happening, plus allows us to make predictions of unforeseen stuff. So if I had tantalum 4, what if I had tantalum 2? Well, I might say, okay, if you say tantalum 4 is 6, it kind of seems like platinum, and then tantalum 2 is like platinum 2, which would be 4. It's pattern recognition, right? You see a pattern, and then you try to repeat that pattern. But that's not theory. And that might be a law. You might say the law of this or that. And then what dictates? Copper 2 can be 4 or 6. These are coordination numbers, by the way. Coordination numbers is how many bind to it. And so which one is it? Is it going to be 4 or 6? How can you predict which one it is? Well, the theory that underlines these complexes is we have to apply the full MO theory. Are we going to be applying the full MO theory? No. Because if we apply the full MO theory, that's quite difficult. And so we aren't going to do that. And so all we're going to do is we're going to stop here. If we want to answer these types of questions, then we got to look at the full MO picture, which we aren't. And so we're going to just look for simple patterns that we can use to help us predict, rather than breaking out the computer and doing full-scale calculations. And so the whole point of this, talking about this, is to, we always want to make predictions, and VSEPR is always a nice thing to do, and hybridization and all that stuff, but we aren't going to use those to understand this. And so these are the typical structures. When something is has two binding, this is, I don't like the way Petrucci does this too, because do you see the lone pair? And then you see a line here. Usually the line represents a bonding pair. And so it looks like there's a lone pair and a bonding pair here, but there's not. This lone pair here should have been converted into a bonding pair. So it's double counting the electrons. I don't really like that, because this nitrogen should have no lone pairs once it's covalently bound to that silver. Well, here, silver, lots of questions go unanswered, like, why isn't silver 4 coordinate or 6 coordinate? Well, we'll just have to look at the patterns that are observed in nature and just recognize those patterns at this point. Zinc 2+, this is a little easier to understand. We're going to come back to zinc 2+ later, but one special thing about zinc 2+ is the electron configuration. What is the electron configuration of Zn2 plus? Zn2 plus is argon D10. So it's got a filled D shell, subshell, I should say. And so it behaves more like you'd expect it, but this we could apply Vesper to. But platinum, we can't. Why can't we apply Vesper to platinum? There's reasons for that. The reasons we'll come back to when we look at the theory underlying these a little deeper. It has to do with the d electrons. Cobalt, 6 coordinate. And so we look for patterns here, you know, 2, 4, 6 as far as the numbers go. You know, and then we see platinum here. Platinum 2 likes 4, platinum 4 likes 6. You know. And then we look at the patterns for the Lewis bases, or you know. As far as the Lewis bases go, these are all what we call monodentate bases because just one atom will bind in the base. And so oxygen will bind from water. When oxygen binds, we call it aqua. There are 4 that you have to memorize special names for. We don't call ammonia, we call it, carbon monoxide, we don't call it carbon monoxide anymore. We'll call it carbonyl when it binds. The nitrogen monoxide is called nitrosyl, nitrogen monoxide and nitric oxide. Do you recognize this one? This is a very good methylamine. This amine, how do I know this is not ammonia amine?
Because
It only has 1 M versus 2 M. This is another amine. This is amine with a 5 carbon ring. It's called, actually, 6 carbon, 5 carbons and 1 nitrogen, 6 atom ring. Pyridine. And these are your standard anions: fluoride, chloride, bromide, iodide, oxide, hydroxide, cyanide. And what we do with this is when they bind and they form that covalent bond, we change the name. And so we call it fluoro instead of fluoride. You know, like if it were ionically bound, we'd call it fluoride. Chloride, when that's covalently bound, etc. So all we do is just change the ending to an O ending. Sulfate. Sulfate, what is that? Is that monodentate or bidentate or tetradentate? You know, when you look at sulfate, shouldn't sulfate be bidentate or maybe tetradentate? And put the metal here and have the 4 bind to it. Then it looks like tetradentate. But when we look at that, we look at the oxygens. The oxygens actually in sulfate are going to be like this. And so if this oxygen is sp2, is that orbital pointed at the metal? If I put the metal here, am I going to get those electrons being donated to the metal? No. And so maybe I'll put the metal over here. If I put the metal ion over here, then this is an sp3, and I run into the problem. Can I have both these oxygens bind at the same time? And so sulfate, even though it has 4 donor atoms, only 1 can bind at a time because of the geometry. And so that's going to be monodentate. Thiosulfate is we just replace one of the oxygens with the sulfur. And then thiosulfate will look like this. With the same situation, only 1 of those atoms will bind. So it's monodentate. We'll call it sulfato or thiosulfato. Nitrite. Nitrite's interesting because nitrite, there are oxygens that can donate. And so nitrite looks like this. And there's a lone pair on that. This is not an amine. Why don't we call this an amine? Is that right? Maybe this isn't right. No, this is nitrate.
Yeah.
That's supposed to be nitrite, sorry. Yeah, why don't we call this an amine? We don't call this an amine because usually the nitrogen is going to be bonded to a carbon or hydrogen in amines. Right? We have nitrogen bonded to oxygen. Oxygens have quite a bit different electronic characteristics. But in any case, we have an oxygen with a negative formal charge. This is 0, this is 0. So which oxygen would be better? The bottom one. But we know that there are two resonance forms, and actually the two oxygens are really the same. But when we do the hybrid, if we were to attach the hybrid, then it gets messy. And so I'm not going to do it. You just pick one resonance form and bond it. But nitrogen is also a good donor. And so nitrite, can either bond this oxygen or can bond the nitrogen. It can't do both at the same time because of geometry. And so if it bonds the nitrogen, we call it nitrito-N-. So nitrito-N, the metal attaches here. Nitrito-O, the metal attaches on the oxygen. Thiocyanate's the same way. If we look at thiocyanate, it can either bond the S or the N. Both have lone pairs. And so if it bonds the S, we -S-. If it bonds the N, we just indicate it with an N rather than an S. And so those are some Do you know what this one's called? This one, do you recognize CH2, What's that? Yeah, ethylene. And so this is ethylene. Is this an amine? Do you think that's an amine? Well, it's got an N. Just look on the right side here. Is that an amine? Yeah, it's an amine. How about this one on the left? It's the same. It's an amine. And so do you know what we call this molecule? Yeah, ethylene diamine. All one word. And so that's the ethylene diamine molecule. It's spelled out here, ethylene diamine. But ethylene diamine has two donor atoms. Is this monodentate or? This is bidentate. And ethylene diamine has no problem being a bidentate ligand because let's put the metal up here and let's bond this to a cobalt 3+. Some of these pens are fresh. So if I have a cobalt 3 here, let's attach one of the nitrogens. So I'm going to convert the lone pair on that into a bonding pair that leaves a hydrogen and two hydrogens and a carbon. And then this carbon has two hydrogens. It's going to go to two hydrogens here. And then I have another nitrogen. Now, will this second nitrogen bind? Well, let's take a look. If I bind the second nitrogen, then I have a 1, 2, 3, 4, 5-membered ring. With a 5-membered ring, is there strain? Are the orbitals properly overlapping? Yeah, so this is not a problem. Ethylene diamine is what we call a bidentate ligand because this single base can bite in two places. It's hard to break off, harder to break off. And so it's also called a chelating agent. Now, what do you think methylene diamine looks like? Yeah, one CH2 group rather than two. Do you think methylene diamine would be a good bidentate ligand? Why not? Right, if I lost one of these, do you see it's going to become a 4-membered ring, and then the bonds are going to be weak and strained, and you'll break one off easily, and it'll stay broken off easily. And so methylene diamine is monodentate, ethylene diamine is bidentate. What comes after ethylene? Propylene. Propylene diamine should be Bidentate. Bidentate. It should be bidentate because that's going to make a 6-membered ring, no problem. 7-membered ring, no problem. So the bigger, the should be no problem. Okay, what do you think of this ion here? This is the oxalate ion. Do you think it's going to be bidentate, monodentate, tetradentate, tridentate? What do you think? Monodentate, because when this one bites, this one can't because it'd be a 4-membered ring. And so monodentate? Yeah, if this one bites and this one bites, how many membered ring is that? 5 is 5. The 5's no problem. And so 5-membered ring is good. But what about these two? Can these two wrap around and bite? No, because this is sp2. This whole thing's sp2. This is flat, and so these electrons are pointed the opposite way. Anyway, so oxalate is an example of a bidentate ligand. And oxalate's an ion, so we changed it to oxalato here. Okay, and then we have this other one, ethylene diamine tetraacetate. Ethylene diamine tetraacetate is an example of what? Monodentate, bidentate, tridentate. Well, if this oxygen bites, can this one bite? No. If this oxygen bites, can this oxygen bite? Yes, no problem. But you know, this molecule's flopping around, this ion, and so can this nitrogen curl around and bite? Yes. And if this nitrogen curls around and bites, can this nitrogen curl around and bite? Yeah, and then an oxygen, and that means it's a hexadentate ligand. This hexadentate ligand we know before from its abbreviated formula. Its abbreviated formula is EDTA 4-. We also like to abbreviate ethylene diamine because ethylene diamine is a bit of a pain to write out. And so it's abbreviated EN and oxalate. These are just for formulas. These aren't for the names because names we have to write the complete name out, ethylene diamine. And so let's go on to naming these things next. All right, let's just look at the homework. Write the formula and name of a complex ion having chromium 3 plus as the central ion with 2 ammonia molecules and 4 chloride ions as ligands. All right, when we write the formula for complexes, we show it with square brackets. The square brackets just indicate what's all covalently bound together. And we start off with the central metal, chromium. And then we write the ligands that attach to it. And so here we need 2 ammonias and 4 chlorides. And so does it matter which one I write first? Should I write the chlorides first or the ammonia first? Yeah, it matters. I write the chlorides first. And so that will be Cl4, like this. And the reason we write the chlorides first is because the metal, well, actually the metal comes first. And then as far as the ligands go, the anion ligands first. And if we have more than one anion ligand, we'll do it alphabetical. If more than one. Okay, followed by the neutral ligands. And if we have more than one neutral ligand, then we go alphabetical. Yeah. And so here the chlorides come first, and then I need the 2 ammonias here. Yes. And that's it. And the next thing I have to figure out is what is the charge on the whole species. And so chromium is +3, chloride is -1 times 4 is -4. And so +3 minus 4 is, and these are neutral, is negative. And so this is an example of a complex anion. We have complex anions, complex cations, and neutral complexes. And so let's look at some other examples of those from the book here. We have, it depends if it's an anion or cation or neutral. And so for complex cations, we just name it like this. Okay, you can see the essential metals written first, followed by the ligands. And here we have no anion ligands, so we just write the neutrals. And then the square brackets indicate what's covalently bonded together. And so this would be called hexamine cobalt 3. And so the name is kind of funny because you don't name the metal first. I'd like to name it cobalt hexamine, but it's going to be hexamine cobalt because we got to name the ligands first. And then the cobalt is going to have a Roman numeral that's equivalent to its oxidation state, so it's 3. Okay, what about this? All right. Yeah. Yeah. Those are. That's good. Why didn't you name the chloros first? Why did you name the amines first? Yeah, because the name, it doesn't matter whether it's an anion or neutral. You'll name it alphabetically. And so here we're going to go with diamine tetrachloro. Chloro. Because the chloride's actually covalently bonded, so we'll call it chloro. Also, a chloride which is going to act as a ligand will be called chloro. Okay. Yeah, and then it's going to be cobalt, and the oxidation state of cobalt is not 1. The net charge is -1. But the actual oxidation state of cobalt is +3, and so it'd be cobalt 3. But there's one other complication, and that is with anion ligands, just like anions, a cation, sodium, it's called sodium. An anion, chlorine, is not called chlorine, it's called chloride. And so when we have anion complexes, we're going to change the ending. And the way we change the ending, well, it's always going to end with the metal. And so to indicate it's an anion, we're going to change it to cobaltate. Rather than call it cobalt, we'll call it cobaltate. And when you hear that 8 ending, that tells you it's an anion that we're dealing with. And so the name of this would be diamine tetrachloro cobaltate 3. So let me write that out. That's all one word. There are no spaces there. And so diamine tetrachlorocobaltate 3. Now, I do it a little bit differently than Petrucci, and I'll tell you why pretty soon. But Petrucci names it alphabetically according to the formula. And so we'll see an example of this in a little bit. I don't care which way you do it. You could either do it alphabetically according to the name or according to the formula. All right, when we have a cation complex or neutral complex, we don't have to change the ending. Just like when we have a cation, like potassium, we don't change anything. And so here, what is this one called? Triamine trichloro, not cobaltate, cobalt 3.
Oh, it doesn't have a.
Yeah, it doesn't have a negative charge, so just cobalt. All right, this is an example of a normal cation. You know, this is a potassium cation and a complex anion. You look at this anion, what's the net charge on the anion? If we have 4 potassium cations, it's got to be a -4 net charge on this. All right, so let's name this. Well, this is an ionic compound. Will we name it tetrapotassium?
No.
No, for ionic compounds, we just say potassium. This would be potassium space cyano, hexa, because cyanide's the anion, so we got to change the ending. Hexacyano iron, but this whole thing's a negative anion complex, so we have to change the ending. So we'd call it, rather than calling iron, we'd call it ironate.
How is that negative? How is that negative?
How's it negative? Because we have 4 potassium cations. So we have 4 potassium cations, and this whole thing must be negative.
Also, they don't put the -4 there.
I'm sorry? No, it doesn't show up because this would be like potassium phosphate. You know, potassium phosphate would be K3PO4. And so it's the same kind of thing. It's just this is a polyatomic anion. And with a funny name. And the funny name is hexacyanoironate. But does ironate sound very good? No. Like ironate, tinate, goldate, or silverate. Those don't sound so good. So instead of using the U.S. name, we're going to use the the Latin name or whatever. What is iron? Would be what, ferrum or something like that? Well, ferrous refers to iron 2+. So, well, anyway, what we're going to call it is ferrate. Rather than copper, well, copper, this is normal, copper cuprate. Tin, rather than calling it tinate, we're going to call it stanate. That sounds a little better than tinate. Argentate, plumbate, and orate. And so these are the ones you just have to remember. Because, and then it's not too hard to forget because leadate just doesn't sound right, or goldate doesn't sound right. And so let's go back to this complex. This complex we're going to call hexacyanoferrate. And what's the charge on iron? I know the whole thing is -4. And so the way I'm going to figure that out is each cyanide is -1. We have 6 of those. That's -6 plus 2. And so this has got to be ferrate 2, Roman numeral 2. Let's look at some other names and see if they make sense. This is a complex cation with a normal anion. The anion name's easy. What is the anion name? Chloride. Why isn't this chloro? It's not a ligand. This is not covalent. What's covalently bound is what's within the square bracket. And so I can easily tell that this has got to be chloride ion, not a chloro ligand. Okay, now when we name this, what do we name? The amine or the sulfato first? The amine. We're going to do it alphabetically. Even though sulfato is written, why is sulfato written first then? If we name, because when you write the formula, anion ligands come first. When you write the name, you don't care if it's an anion or neutral. You're going to write all of them alphabetically. And so, only time you care whether it's an anion or neutral is writing formulas. Writing names, we don't have to worry about that. Too bad, you know, too bad they just didn't make the rules consistent, self-consistent. But anyway, this would be called pentamine. Now, no, do you use a single vowel or double vowel? So, is it pentamine or pentamine? some people are sticklers for this. So some people, when you write the double vowel, they go, no, 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 don't write double vowels. Call it pentamine rather than pentaamine. I usually use double vowels. So pentamine, sulfato for sulfate, chromium, and the charge on chromium, well, sulfate's -2, amines are neutral. Chromium must be +2. No, +3, sorry. +3. If it's +3, it's going to give this whole thing a +1 charge, and we need 1 chloride to balance the charge. And so pentamine, sulfato, chromium 3 chloride. Is there a space? Yes. There's a space here because we always have to have a space between the cation name and the anion name. Okay, here's another example. Okay, this is another complex cation with a straightforward anion. The anion we know, that's the sulfate. And again, this is not sulfato, this is just plain old sulfate. And so this would be
pentamine, chromium.
3. Well, it's got to be, sulfate's -2, so this whole thing has to be +2. Chloride's -1, therefore this has got to be +3. So again, it's a 3. Did you guys already do these examples in the book? Maybe I should move to the homework. Some of you did. Probably not. This is 24-4. Let's take a look at this. Pentamine. Okay, A comes before N. So pentamine, nitrite. Nitrito, because nitrite is an ion, so we change the ending. Amine is not an ion, so we don't call it amino. We'll just call it amine. Nitrito. Now, what's bonding? Is it the N or the O? The N. Usually if the N's written like this, NO2. If the O is bonding, we usually write it ONO. And so it would be nitrito hyphen N hyphen cobalt 3. It's got to be cobalt 3 because 3 minus 1 gives me +2. Yeah. How do we know when the O is bonding? Well, that's shown here. Pentamine, nitrito, O. And so it's written differently. Cobalt 3. All right, we're going to go back to the homeworks here, and let's do some of those. Let me flip back. Okay, let's name some of these here. Okay, it's not cobaltate, but it's cobalt. The A is positive, so we don't use it. So hexamine cobalt 2. What about this one? It's not hexafluoroaluminum, it's hexafluoroaluminate 3. Now aluminate 3 is okay, so we don't have to change that. Aluminate 3. And the 3, it's not the 3 because of the 3 negative, it's the 3 because of the 3 positive, which is going to neutralize 3 of the 6 negatives, give us a net -3. How about this one here? Hexacyanocuprate 2. That's good. Now, is hexacyanocuprate 2 going to be tetrahedral or square planar? Don't know, because we need the theory, right? But what we could do is we could use patterns. And the patterns, we go back to this chart here and see, You know, is copper 2 usually square planar or? Well, it doesn't say. It says copper.
204.
It could be either 4 or 6 coordinate. That's 4 coordinate. And so that means it could either be tetrahedral or square planar. And so then what I do is I flip through here and see, do they have any copper 2 structures? Are they square planar or 4 coordinate to see what the experimental data shows? And I don't see any. And so what would I say? Well, don't know. But I do. I know because I've seen them before and they're square planar. But I wouldn't expect you to know. At least not yet. All right, here. Later on, we'll see. I could have predicted it too, because I'm going to give you a little more theory when we get back in the latter sections of this chapter. But what about this one? What comes first? What is the charge on chromium? 1. No. The net charge is 1. The charge on chromium is 3. Yeah, 3 minus 2 gives us plus 1, so it's 3. Now, what is the coordination number? This is monodentate ligand, so the coordination number is 6. Coordination number? Coordination number? 4. Coordination number? So those coordination numbers are pretty easy. How about the coordination number of this? What's the coordination number? The coordination number of this is 6. Do you know why it's 6? Because OX stands for oxalate or oxalato, and oxalato is a bidentate ligand. And so if I have 3 of these, and each one bites in 2 places, then there's 6 bites in there. And so the coordination number is 6.
Why is it written like OX?
Why is it written OX?
Oh, that's an abbreviation.
That's an abbreviation. You're allowed certain abbreviations to save time. For oxalates, it's not a big deal. I mean, oxalate C2O4, that's not so hard to write. But C2O4, 2 minus, is written OX 2 minus. But what about naming this? Tell me, is it okay to use the abbreviation in the name? You know, I'm going to use the abbreviation in the name. I'm going to call it triox cobaltate 3. Now, when you name it, you're not allowed these abbreviations, only when you're writing the formula. And so this would be trioxalato. We'd have to actually spell it out. Trioxalato cobaltate. What's the charge on cobalt? 2. It's cobalt. And so this is trioxalato cobaltate 2. And so we got a cobalt 2 plus stuck in the center. And then we have an oxalate bonded to this. And so we got the oxygen here, 2 lone pairs, like this. And so that's 1 oxalate binding in 2 places. This is why bidentate. And then we have another oxalate here. But you know what? There's one other abbreviation you're allowed. And that's when you're drawing the structure. You're allowed to link these 2 and write an OX like this. And so this link like this and an OX is equivalent to this. And there's one more abbreviation that's common for this, and I kind of screwed up the geometry. But the other one is where you just kink it like this. So I draw, this is kind of like in organic chemistry, they kink it like this and then kink it like this to show it. Do you see that? Yeah. So I don't show the carbon atoms, I just show the carbon bonds. I shouldn't have drawn it like this because this bond goes behind this oxygen, so that's why it looks kind of funny. Anyway, the coordination number 6, trioxalato cobaltate. How about the coordination number of the next one? What's the coordination number here? 6? No, 6 is wrong. Well, thiosulfato. No, thiosulfato is like sulfate. Sulfate is a bidentate, monodentate, tetradentate, tridentate, sulfate. Look back in your notes. Sulfate is monodentate. All you're doing when you make a thiosulfate is you replace one of the oxygens with a sulfur. And so it should be monodentate. And so the coordination number of silver is 2. And what is this called? Thiosulfato silverate 1? No, dithiosulfato argentate. Argentate 1. Each thiosulfate is minus 2. And so we've neutralized one of them. All right, let's go on to this next one. How would you name this? Yeah, so we have hydroxoaquaamine. So not hydroxo, but aqua versus amine. Which one are we going to name first? Amine. Right.
Aren't you saying tetra-aqua?
I will. We're going to say, we're going to call this amine tetra-aqua hydroxo cobaltate. Cobalt or cobaltate? Cobalt. And the charge? 3. Because hydroxide is minus 1. Now, there's a conflict here. This is Petrucci. Petrucci, remember, if we have more than one neutral, we order those alphabetically. And so these both are neutral. And so what comes first, amine or aqua? Amine should come before aqua. And so the reason why he writes aqua first is because he does it alphabetically according to the first element in the formula. And so when he sees aqua, he sees hydrogen. When he sees amine, he sees nitrogen. And so that's what he's doing there.
Wait, so what's the name?
The name is amine tetra-aqua hydroxo cobalt 3.
Just do the alphabetical directly.
Yeah, you know what? Just do the alphabetical according to the name. You know, otherwise, the reason why I have you do this is because what do we write as the formula for ethylene diamine? How should you write that formula? Should you write it H2NCH2CH2NH2? If you write ethylene diamine like this, then hydrogen is the first element. But sometimes people like to write it like this, NH2CH2CH2NH2. If you write it like this, then nitrogen is the first. Right? But a lot of people don't like to write it like this because this is a condensed structural formula. Lots of people like to use the molecular formula. The molecular formula is C2H2468, H8N2. Have you seen molecular formulas like this? If you write it like this, then the first is carbon. And so which one do you do? What's the rule? So we need another subset of rules to help us guide us through this. Well, it's starting to get too complicated. And so the reason why, and I don't care so much because the rules aren't fixed in stone for these complexes. In fact, 10 years ago, they wrote the neutrals before the anions. And so if you look at all the bottles labeled 10 years ago, they're backwards from today. And so there's continuing argument about how to properly name these things. So I just have given up about trying to come up with a subset of rules for this and just say, just name it according to the name. What is the name? Because we have one more. We have the abbreviation for ethylene diamine, which is EN. And so, you know, just name it according to the name. Or, alphabetize it according to the name. E. You know, ethylene diamine rather than H, N, or C. and everybody will know what you're talking about. And nobody's going to really criticize you. So there's a lot more flexibility in these names here. The thing is, just be consistent. I don't want to see on one name you follow this rule, and then on the very next one you follow a different rule. I just want to see the same rule follow throughout. All right, so let's continue here with this. So this is why aqua came before amine. You know, if you follow my rule, you would have written amine first, and then the aqua. All right, how about this one? Good. Cobalt 3. Okay, how about this one? Okay, this is going to be tetra aqua platinum. Now we have a choice. Platinum 2 or platinum 4? Oh, we don't know. Yeah, the previous one is nitrito hyphen O hyphen. And then this is going to be hexa chloro platinate. Now, is it going to be platinate 2 or platinate 4? So either, if the first one is 2, then the second one's 4, it works out. If the first one's 4 and the second one's 2, then it works out. They have to be one or the other. But here, what we're going to do is we're going to use a little bit of experimental data to help us. And so we flip back over here. Does platinum 2 like 4 coordinate or 6? And so here we look at platinum 2 likes to form 4. Platinum 4 likes to form 6. And so flipping back here, I can tell based on what's been observed in the past, which is which. You know, it'd be much nicer just to have a theory to figure it out, but this platinum is 4, and this platinum must be 2, because this is 4 coordinate, this is 6 coordinate. Both of these are monodentate ligands. And so when I ask you, what is the coordination number of platinum, here it's 4. But, you know, sometimes people write 10. I don't know why they combine these. This one's 4 and this one's 6. Okay, let's go here. Diaqua. Dioxalato. Ferrate. No, oxalate's -2. 2 minus 2s is -4. These are 0. So -4 plus what gives me -1? Plus 3, so it's ferrate 3. How about this one? This is just your normal silver ion, this +1. So this would be silver, tetraiodo, mercurate, 2. That's correct. All right, let's try writing some formulas here. Potassium hexacyanoferrate. And so if we look at potassium ions, what's the formula for potassium ions? K plus. What's the formula for hexacyanoferrate? Hexacyanoferrate is a complex. And so what comes first, cyanide or iron? Iron. And the charge on this? It's ferrate, what is it, ferrate 2 or ferrate 3? Ferrate 3. So +3 minus 6 gives me -3. And so I need how many potassiums to balance the charge? 3. So it's going to be K3 FeCN6. Potassium hexacyanophthalate. All right, there's an alternate numbering scheme. Have you heard of bis, tris, tetrakis? Bis is the same thing as di. Tris is the same thing as tri, and tetrakis is the same thing as tetra. And so we have two alternate systems. The reason why we have two alternate systems is because of this. Okay, imagine if we use di rather than bis. And so let's call this diethylene diamine. Well, don't look at that and listen to this. Diethylene diamine. If you heard diethylene diamine, are you talking you have two ethylenes and two amines? Yeah, that's what you think. Two ethylenes and two amines. But it's not. It's two ethylene diamines. And so when we have a ligand with a di or tri or prefix in its name, we try to avoid confusion by using the secondary numbering system, which is bis. So if we call this bis ethylene diamine, if you hear bis ethylene diamine, you think two ethylene diamine molecules. If you hear diethylene diamine, then you think two ethylenes and two amines. And so this is why it's required. And so we wouldn't call this diethylene diamine. And to further reinforce that, take a look at the parentheses. They put parentheses around the ethylene diamine to make sure that it's concrete that we're talking about two ethylene diamines. Copper 2 ion. And so let's go ahead and write the formula for that. And so what comes first? The copper, and then we have ethylene diamine. Now you have different choices for writing ethylene diamine. I just erased them here. But you're also allowed the abbreviation in the formula. You're not allowed the abbreviation in the name. And so this would be Cu and then two of these ethylene diamines, like this. And the net charge? Ethylene diamines are neutral, so this copper 2 plus and 0 goes 2 plus. What would the structure of this look like?
Where's the amine?
Where's the amine?
In the class of E and...
You mean where's the NH3? Yeah. Yeah, the EN is ethylene diamine, the whole thing. Okay, or you write in the formula. The formula for ethylene diamine is, NH2, CH2, CH2, NH2. It's too long.
But in the tab we can just write EN.
Or you could just write it C2H8N2. But the problem with C2H8N2 is this. You have lots of isomers. Isomers are the same formula, but different structures. So we have to lay out what the structure is. This is the structure. And so this isn't always good because is this ethylene diamine or some other structure? And some other structure is going to have different properties. And so that's why it's allowed. Now, if we were to draw out the Lewis structure of this, it looks something like this. We put a copper 2 plus in the center, and then just attach one ethylene diamine. Well, attaching ethylene diamine, it's a bidentate ligand. Forms a 5-membered ring, so it's not a problem. And that would be it. But that is, it's a lot of work. And so what people do is they're allowed this abbreviation. They draw a link between these two bonds and write EN. There's an alternate way of doing this, too. The alternate way that you can see sometimes is like this, where you ignore the carbon atoms and the hydrogens, and you write it like this. This would be an ethylene diamine as well. And so this would be bisethylene diamine, copper 2. Take a look at E. Trisethylene diamine. All right. If you see trisethylene diamine, iron 3, what's the formula for that? Let me erase these. Yeah, it would be Fe, and then 3 ENs.
CN6
Bracket. Okay, but what is the charge on this? Plus 3. I'm not going to draw the bracket next because I want to figure out what the ratio is. You know. But what is the coordination number on iron? Coordination number is 3? 6. Coordination number is 6. And then what's the other ion? Hexa. Then hexacyanoferrate. We already know. Hexacyanoferrate is a 3 minus. And so these are going to combine in a 1-to-1 ratio. Oh, wait a minute. It's hexacyanoferrate 2. I'm wrong. These are not going to combine in a 1-to-1 ratio. It's plus 2 minus, plus 2 minus 6 gives me 4 minus. And so what ratio are they going to combine in? Okay, if I do 2 of these, will it balance? No, so I'll do 2 of these and then 2 of these. Will it balance? No. Yeah, and so I'll do the trick of cross multiplying. FeEn 3, 4, FeCN 6, 3. And then it's charge balanced. Right, so we go until 5. Then I forgot the quiz, right, so far this week. So we need at least one quiz. We'll just make it a 2.5 pointer. How about that? Your first quiz, we aren't going to put too many points in. It's going to take me a little bit of time to adjust to this daily quiz thing. And so let's see what we want to do for a quiz. You don't need a very big piece of paper, just a small sheet. I'll bring in some small sheets for future quizzes. Okay, so are you guys ready for the question? No, this is going to be from yesterday's and the day before that and the day before that. So I'm trying to remember what I talked about. All right, ready? All right, here. And draw the Lewis structure. Oh my God. For NaCl.
We don't have to write down the question, right?
No. Is this ionic, covalent, Yeah. The 2.5 points.